Good evening everyone. Welcome to this institute lecture to be delivered by Professor Sanjay Sampath. I am Ashutosh Gandhi from Metallurgical Engineering and Material Science, and it is my privilege to introduce today's speaker to all of you. So Professor Sanjay Sampath is in the Department of Material Science and Chemical Engineering at Stony Brook University, and he is the director of the Center for Thermal Spray Research at this university, which was started initially with NSF funding under a very select MRSEC program, and he continues to support and direct this center further to greater glory. Professor Sanjay Sampath has achieved a very rare mix of industrially relevant research and basic science in the field of thermal spray, and he would like to emphasize the industry, that translational research which goes to the industry in today's talk. He has been recognized for his contribution to the field of thermal spray and material science and engineering by many eminent professional organizations such as the American Ceramic Society, ASM and ASME. So it is my privilege to now invite Professor Sanjay to deliver this institute lecture.
Thank you, Ashutosh. I think they can only stand in the middle. That's okay. Okay. Well, it's late in the evening, so hopefully we'll have some fun here for a little bit. If you have any questions, feel free to ask along as we go along. I'm from Bombay. I grew up here, so it's always nice to come to Bombay. I've been coming on a regular basis. So what I'm going to do is give you a little bit of a partially non-technical talk, and I'm hoping that especially those of you who are young and are looking for careers, think about this in a kind of a different way. As Ashutosh already talked about, I'm a one-trick pony. I've done the same thing for 40 years, but that also has some benefits in doing that. So let me first talk about sort of, we all go through what we call midlife crisis. Some of you are young, will come to that thing at some point in time. But first I want to kind of talk about, if you're going to work with industry and if you're going to make work relevant, you need to think about the word innovation, right? And you've heard of a lot of these words here: invention, patents, venture capital, like some colleagues here, billionaires, things of that kind. So there's this word innovation has become very, very popular now everywhere, from the politicians to corporate types. And every future engineer, worker has to think about the word innovation, because that's the only way you're going to survive in a global market. And there are lots of products that are encroaching. This is an old slide, but the important thing here is the products that you didn't know you needed until you saw it, then you can't live without it. And that's kind of a true statement for some of us who are older. When I was doing my PhD, I didn't even have a computer. And by the time I'm done, I'm sending emails from my phone in Jay's office a few minutes ago with a large, file. So, in your career, you'll see lots of things happen very, very quickly, because the pace of acceleration is incredibly fast. And I'll show an example of that. So I think what I'd like to, the take-home point is, how does it affect me, right? And this is something that I started to think about. Where do I fit within this innovation ecosystem? What's in it for me? Can I become rich? And more importantly, I tell my students and my children, everybody, is your organization innovative? If your organization is not innovative, your organization will not exist, right? There are plenty of examples of companies. Big companies have gone bankrupt, right? Like General Motors, for example, one of the world's largest companies. Because there's always competitive threats, and then there's globalization. If something can be done cheaper, faster, better somewhere in the world, it will get done cheaper, faster, and thus, and won't be done here. That's part of the advantage also, because India is becoming part of the global circuit. So, and also it's very important for those of you who are thinking of ideas that invention is not innovation, right? Innovation is basically how you create value. So you can have lots of inventions, but it doesn't have to work. An innovation has to work. It has to completely affect how you live in that process. So, and this is a very simple graph, and I'll explain this better. So invention is not enough. And that also applies to basic science. A lot of you are doing your PhDs and things of that kind. If you just do the science, and what is the impact of that science, has to be considered. So innovation is basically, whether it's your idea from science or from invention, it's how you put it to use, and do people buy your idea? If people don't buy your idea, then it's not an innovation. So as I said, invention without innovation is pastime. It's a hobby. And there's a lot of curiosity-driven science, which we all do. I think it's very important, but that may not result in innovation, right? But what's happening is more and more, even corporate leaders and political leaders are always asking, well, why am I giving you this money? What am I going to get out of it? Initially all these ideas look like, oh, it's impossible, but then, I said it was a good idea all along. Now, so innovation is now talked about quite a lot. You have institutes for innovation, and I just saw today something about value proposition creation. The thing is, there's a very important article I read many years ago called "Why is Facebook Killing Silicon Valley?" So what happened was, until the era of Facebook, people made money by investment, but it took a long time. And then comes along a guy sitting in his pajamas in his dorm room, and he makes $1 billion because his ideas scaled quickly. And so the internet has changed the way we think about return on investment. So people want very rapid returns on investment, and if you're going to do that, if you don't promise that, then they won't give you the money. So, this idea of doing things in software and business practices and finance, you don't have hard problems that are connected. So the area that we are interested in is complex engineering systems. And what do we mean by complex engineering systems? The picture shows it, right? Nuclear plants, aircraft engines, space, oil and gas, automotive, things of that kind, where these are highly integrated. They contain many subsystems. And majority of our lives revolve around power, mobility, food, medical, and so on and so forth. And the word innovation in these complex engineering is a much more difficult. Because these interactions of subsystems, if you come up with one idea, it might affect another one. For example, let's say you came up with a new braking system for your car, right? Then the question is, what else things in your car you have to change to accommodate that braking system? So your idea is not sufficient. You have to interact with others. The risk is very high. You make one mistake, it can, cause a plane to crash. And in order to meet this, you need a much larger requirement. And what that does is it takes very, very long lead times and very long payback times. And if you ask anybody, whether it's a corporate head or which is a financier, what you will find is nobody's got patience for this anymore. And part of the reason is, if something is going to take 15 years, you don't know what the value of the rupee is going to be in 15 years. So you don't want to make that investment. So there's a lot of stagnation in that. So the only party that supports this is actually the government. Only the government is dumb enough to accept this, but also they know that's the reason why they do it, because if they don't do it, nobody else will do it. And so you got lots of people to satisfy: shareholders, managers, lawyers, human resources. And then if you have a good idea, you're a college student, who are you going to call? If you call General Electric or Pratt & Whitney or General Motors or Tata Steel, whoever, how are you going to tell them your problem, and who in that company is going to listen to you, right? I just talked to one of the colleagues about that. And then if they like the idea, then if they're going to pay for it, they're going to own it, right? So you just lost most of your idea. So this is a very difficult problem. And remember, I used the word personalizing the innovation world. This is how I got affected, because I had a bunch of good ideas, and it was very difficult to translate those good ideas into industrial practice. So how do people do things? So one is research-based. So you're all sitting in labs, you're doing some nice research that becomes translated into development, then the idea goes propels, you make a product, you support, right? This is sort of what we call bottom-up. Or you do market-based. That is, you know that there is a problem, and Mr. Roy was telling me about medical implants. You have an aging population, you have a large aging population, you know that there's going to be need for implants. And so that drives investment, because you know that there's always going to be somebody who's going to need that idea. So this is more predictable. This is where investors like to put money. This is where government puts money, because they know if they don't, nobody else will do that. So the idea of classic research R&D in a company is almost gone. There used to be Bell Labs and IBM Watson and GE Research and Xerox PARC and Kodak, all these companies that had research, General Motors research, they don't even exist anymore, because there's really this big plate and a big void, because the financial folks are much more comfortable because they can predict a return on investment on a market-based approach. But the problem with the market-based approach is everybody knows, so that then you're going to create competition. So typically what happens in innovation is we follow what's called a technology S-curve. You plot something like a value here as a function of time. You come up with an idea, you got to make it work properly, improve performance, efficiency, reliability, cost, and then the product becomes mature. This axis takes money, this axis takes time. Both are very difficult to get a hold of. I managed to get one of these for, it's a relatively old graph, and it plotted the percent of US household adoption of a technology since its inception. So this is in years here. So if idea was invented here, how long did it take to populate through the entire population? So if you look at automobiles, this is a dated graph. First of all, for 25 years, very few people had a car. Then it took a long time for the population to buy that car. Airplane, even longer. It took 45 years for people to start to adopt these cars. Television was a little bit sooner. The cost is smaller. Microwave, and so on and so forth. So what you get is, this is what we call the hockey stick, right? A reverse hockey stick. Basically, everybody wants to be on this portion of the hockey stick. That means you're growing very, very rapidly. And that's what people want. Now look over here, there's internet, cell phone. They're much shorter time scales. But what people forget, that there was about 20 years of investment in microchip manufacturing and wireless and all of that. And even the internet was started by US government programs, ARPANET, and I forgot what the NSF net was called. So by the time the population got it, there's already been some 20 years of work that was already done through government funding. And so if you're going to do anything in your career in the future, you have to think about sort of what's that incubation time and whether you'll even get there, right? So where does your technology fit and interest in that context? So this is what I call personalization. So whatever is your interest you're working on, high entropy oxide, biomedical implant, whatever you do, see if you can put it in this framework, and it's actually kind of an eye-opener, right? So my area of interest is thermal spraying. As I said, I'm one-trick pony. I've done this for a long time. The nice thing with thermal spray, it never gets boring, and you'll see that in a second. So what is thermal spray? For those of you who don't know, we basically take powders or wires or rods, in some cases some solutions and suspensions, and we basically spray it on using some sort of a thermal device, right? A flame torch, a plasma torch, something that will melt and propel particles at a high speed. And what happens is these tiny particles, they're about 50 microns, 30 microns size, they impact and they become a small pancake. They're of the order of about 100 microns in diameter, maybe a micron or so thick. And then you stack these particles one on top of another, you end up getting a coating. So what happens is you basically become like a painter, right? You're spray painting. And so we ended up using it as a surface engineering tool to protect metallic substrate. We do thermal spray in lots of different ways. I have a video. I hope it doesn't make too much noise. Okay. So this is an example of a robot that's moving in front of a part or a component. I'll stop that. Basically, you get a picture. Basically, what you do is this is a plasma torch, this is a combustion top, and I'll come back to this later. This is basically to coat the inside of cylinders, and there's a process called cold spray where you use high velocity impact. So since you're depositing the materials, these are not bulk materials. You're basically layering them on top of a surface. And because you're layering them with different processes, conditions, I can take a single process and I can make multiple different microstructures with it. So I can make a porous coating, to a dense coating, to a crack coating, to a layer. So lots of opportunities to do these interesting things. And that's the reason why the process works. It's practical, it's easy to do, and so a lot of people use it. So every industrial sector touches thermal spray. Turbines, majority of the parts get thermal sprayed. Landing gear, this is an example. Pulp and paper, heavy machinery, infrastructure, oil and gas, automotive, biomedical implants, and electronics industry. And that's the power of what we call a platform technology, right? And this is another idea that if you're going to work in a particular industry, choose something that's got a diversity of applications. So that'll help you with making sure that you're fitting into lots of different applications. It's flexible, scalable. This is another very important aspect for manufacturing, right? Let's say your application changes. You don't need a new factory. You can just reconfigure the factory to do that. You want to do, you start off with one small spray cell, you do 100 parts, then you say, I need more, you can add another part. That's what we call scalable. I want to change my material, it's flexible. And so that's the kind of technology you want that allows you to do things in a flexible way. So that's what, if you go back in history and you look at technology, only technologies that have those kinds of features actually succeed. So you really don't want to, try to do difficult things because they are hard to adopt. And so it started in the turn of the previous century. It took a long time. You see the S curve, the hockey stick, that it stays dormant for a long time. Then few people tried, then people pick it up faster and faster, and then it moves in that direction. And a lot of different industrial sectors played around with it, and that's how they built the technology. Now, what happened, you always want to look at what created this sharp hockey stick, because that's when the technology scales, right? And in this example, there was one particular incident that caused this to happen. Pratt & Whitney and General Electric were building what's called a bypass engine. This is 1960s. And they needed a coating to, a lot of these are rubbing against each other. When an aircraft takes off and lands, all these things are spinning. The metals do a fabulous job. All the superalloys, the titanium alloys, the ferrous alloys, the composites. There is so much materials engineering here. It's unbelievable how, it's hard to believe this thing actually works, right? In fact, I was teaching once the class itself based on gas turbines, because if you can understand this, you pretty much understand thermodynamics, fluid mechanics, solid mechanics, heat transfer, wear, material science, chemical engineering, combustion, everything is in here, right? In fact, if you go to a gas turbine engineering operation, there'll be thousands of engineers involved. Basically, it's a very compact and really incredible amount of power you produce. But you can see all these things are rotating, and they're rubbing against all kinds of surfaces. And so what happened was they decided at that time that there are lots of rubbing surfaces. Many of them are operating at high temperatures, and many of them use expensive alloys. That, hey, what if I put a little coating on it, and the coating bears the brunt of that initial impact? So it was considered a sacrificial layer. And so that's why they chose surfacing. The simplest idea was life extension. I'm going to put this part up, it comes back, make sure that my metal, the critical structural alloys are cracked. Then you can reapply the coating without giving away. That's called maintenance, repair, and overhaul. Then you can add other things like insulations, and you can deliberately create surfaces for sealing that rub because things are bouncing around quite a bit. That's how it started. In fact, I met, I think Jaya met him too. A 92-year-old man came and gave a talk. He had put the first coating on one of these parts in 1968. And he was telling us, there was no computer, there were no calculators, you use slide rules, and that's how they built the first coating. Now it's in every aircraft, every engine that you fly has thousands of these coatings that are being used. Nobody knows what they're doing with it, but they're using it. Because all the critical guys who did the thinking were 60, 70 years ago. But we always fancy cool stuff, and so we end up working on, all of us, and in India as well, on these ceramic materials for insulation purposes. So I'll show this graph. This is actually from Professor Sampath, who was an IIT graduate. So if you plot temperature as a function of years, this is now getting into decades, you look at what has happened to alloys. The capability of the engine has grown about 100 degrees in 60 years, 50, 60 years, right? But you see, the actual engine is even hotter than the melting point of your alloy. And the reason for that is you first introduce film cooling, then you put thermal barrier coatings, and now you're doing some ceramic systems with it. So these coatings gave you huge ability to insulate the metal from getting hot. And to do that, you put a ceramic coating on a metal. It's non-trivial because they have large thermal expansion, they heat and cool, so it's a classic example of how something can fail. And so you've got, you need to deliberately create porosity and feathery structure so they can do this during heating and cooling. And so we have to work on processes that help us get there. And second thing is, they're not sitting. Every time a flight takes off and comes back, that microstructure is changing. That's an idea that we're working closely with Professor Gandhi on. And now you're asked the question, why do I need it? Because if you're a boss in a company and says, why do I need this? So I call that need-driven innovation. So it turned out that the amount of heat that was going through one turbine blade, that's the one that does the work, right? You've got explosive combustion explosion on that, what we call the bucket, and it pushes that's how you get propulsion. The amount of air, this is a single crystal, by the way, and it's internally cooled. And the amount of heat loss from one blade, and there's about 86 in each stage, can power 18 homes with electricity. And if I put this thin coating on it, I get 6 homes for free. So that's a nice way to explain to your boss how much money you're saving, right? Another way to do it is that the pull from just putting the thermal barrier coating on a blade is equal to powering, is like a work of one car, if you look at it in horsepower. So these things are incredibly important. Another way to do it, that's for aero engines, this is for land-based engines. These things are much bigger. Like one of these a few of these can power Bombay, and that's exactly what it does. Tata Power has got a few of these in gas turbines that power. And here you put the TBC on, a 1% increase in efficiency can give you 2 million fuel cost, 25,000, right? And usually we target 10%. So you're saving, these numbers are old, I mean, they may be saving tens, hundreds of millions of dollars. So the moment you have an innovation that's proven, you can build another S-curve. So you can see how it's grown from the 1960s, and now 2 to 3 million pounds of zirconia gets plasma spray every year, right? Now it's a real business. Of course, there's a lot of competition, so it's not so easy. And now there's an interest in moving from metal to ceramics. Ceramic composite, and GE just introduced this into their LEAP engines. And again, you need a coating here. It's a different type of coating. I'm not going to talk about that today. But look at the time, 50 years. And even today, majority of the application, they don't think about it what's called prime reliant. Prime reliant means that you rely on that metal. So if a metal fails in one of these applications, the system can fail. They tolerate like one or two, but then I've seen blades come off engines. They're designed, but even then, if you have 2 bird strikes that recently happened somewhere, you can shut down the entire engine. So the idea is that the coating, if it fails, the system should still keep functioning. So the alloys are doing most of the work with the cooling, but the TBC is there. Like one engineer once explained it to me that we call it an insurance policy. I've got a blade that costs $10,000. I put a coating for $300. I get an insurance policy, and I get the benefit of the benefit. I've seen engines that have come off, particularly in land-based. Coating is chipped off in 6 months in some locations because they're very hard to keep them. We are trying very hard to make them more durable and more prime reliant. So that was one example. I'll come back to this in a bit. There's lots of coatings. As I told you, it's a platform technology, so you can use it in sliding wear, and abrasion, and implants where you've got tribological aspects, and things like structural materials and so on. So there's lots of opportunities. So here I'm going to give you the same example in a different way. So a lot of the landing gears, that the high strength steel that basically supports that big impact load, and then the piston goes up and down, right? That's how you stabilize it. Those are made of very high strength 300M structural alloys. But you always have a coating on them because you've got a sliding seal surface on them, and you also have to worry about corrosion. So they were electroplated with chrome a long time ago, from the beginning of the time. But what happened here was, if you, none of the airplane manufacturers cared. They just kept doing chrome plating. But what happened was EU and US about 25 years ago and said, making chrome plate is carcinogenic on the humans, and so we don't want to do this anymore. So people scrambled to come up with a solution that was not using chrome, and that's where thermal spray came up as an idea. And it was quite successful. And then, of course, there was spill-off effect, right? The heavy machinery people were doing, like Caterpillar was making these shafts. They would make them originally in, let's say, in US, but then they send it into India. Then who's going to chrome plate such a large shaft again? And so thermal spray turned out to be more flexible and reconfigurable, and that's why it succeeded. And same for the oil and gas industry. So here the moral of the story is, if we didn't have the regulatory requirement from the government, this innovation would not have been possible. One important thing that really stymied this application is many times coatings are there as coatings, right? If you take off the coating, nothing has happened to the structure. But for all these so many of the aero engine coatings are what we call overlays, that they're just added on top. They don't really participate together with the substrate. But in these kinds of coatings, the coating and the substrate are actually very well bonded, and there's load transfer, there's residual stress, and things of the kind. So it becomes a big problem where you have to worry about fatigue and corrosion and structural aspects, impact. And what happened was they didn't do any new ideas with the coatings. The coatings already existed and the processes existed. But they had to prove, and anything with aerospace, you have to really take a long time. So this is an example of lab testing, and there was a video for an Airbus where they actually would drop this A380 landing gear from like 6 stories and it'll bounce, and that you have to pass that test. And then they would do the in-flight testing. So again, the idea started with Lufthansa in the 1980s. By the time 787 started to put it into their design, it was another 20 years. Again, what has happened recently is that the chrome plate people are not sitting idle. So they came up with ways to make much more, environmentally friendly chrome plating. So now all of a sudden the aero guys say, why am I doing this thermal spray? I can go back to chrome. Right? So that's what I call competitive threat to the technology. The third example I'll give you is really interesting one. This is an automotive cylinder. Many of you have seen an automotive cylinder. And so those aerospace and the aero structures are relatively small volume, relatively, right? There's only a few thousand, tens of thousands of them. When you talk about automotive, you're talking few 10 millions of these things. So it turned out that the original cars were built with cast iron, and they made it out of aluminum. Aluminum doesn't have very good wear resistance. So you wanted to shrink fit or cast in place a liner out of steel. Problem was, any of those things, you need to first buy a liner, and then you got to find a way to bond that liner onto the surface, and they can't be thin. So somebody I knew a long time ago came up with it, why don't we thermal spray the inside, so the thin coating of steel. And it turned out thermal spray actually has some porosity, which is great for oil retention. So it actually made the process better. So this is what they did. They wanted to, instead of using this liner, they wanted to directly spray the coating on it. It actually increased the heat transfer, reduced a knock, and all of those things. But what happened here was that thermal spray wasn't ready for this. Two things. First, they said, oh, I've got a part that's this big. And thermal spray was a stationary, right? I said, you can't ask me to rotate this big block, right? So my friend Martin went to all of these places. Can you make a torch that spins, right? And everybody said, it's impossible. You can't make a torch that spins, got arcs and current and gas and all kinds of things, right? Remember that Arthur Clarke student? It's impossible. It's not worth doing. Oh, it was always easy to do. Turned out 4 years later, there were 4 torches that were spinning. Then the problem was, can you do 24 hours a day, non-stop, because you need millions. Oh, by the way, we cannot do any inspection at all. Whatever you spray has to work perfectly. So all of these requirements, and they said, oh, you cannot mask and all that. There's no time for all that. Continuous operation. Oh, by the way, no nano and all that. It has to be coat hanger steel. It literally is coat hanger steel. You know the coat hangers that they make? And all kinds of things, requirements. It has to be incredibly consistent and things like that. So I'll show you the technology. This might play, my video might play and make noise, but the idea of rotating the part was around in the 60s. Actually, they did this on a small scooter engine in Japan. Started in the 80s, then it sat like this for a very long time because nobody was convinced that this is possible. And then, and all of these cool torches, in fact, one came from our university. Okay, it stopped. It's too noisy. But you see, the impossible became possible, right? And that was actually invented in the early 90s. And then General Motors and Ford actually built a factory, but they never put it into production because the liner guys gave them huge discounts. So you put a lot. So, and then the oil price came down, the CAFE standards were reduced, so there was no really need for doing that. But then came along, Volkswagen was already doing it, and then BMW and Mercedes came and they introduced this idea in one of their mass production lines. And that took off. That's when the technology in S-curve took it. There are 50 million thermal spray cylinder bores today that's running. Mostly, if any of you have the ability to buy a BMW, you can have a thermal spray engine. I don't have one. I need to get one of these days. Used is fine. Then the Mercedes is all thermal sprayed. The Ford F-150, finally the Americans have reintroduced this idea. And you see the curves going back. Why? Because the internal combustion engine is in trouble, right? So electrification means you don't need these complex manufacturing processes. So, I gave you sort of some of the successes. Let's talk about the bad news. You should always talk about bad news or good news. all of this was done from top down. That is, the system demanded, whether it was through performance, remanufacturing, regulatory, or that last example I gave you. Meanwhile, a lot of us academics and researchers, we came up with all kinds of ideas. If you look at the thermal spray graveyard, you'll find lots of ideas, hundreds of patents, maybe in thousands. Nothing has worked, right? Nanomaterials, amorphous alloys, high temperature, right? Solutions, suspensions, things of that kind. And part of the reason is because the implementations are light. So if you don't want to do that, it gets a long, long time. I actually have a book in my office from the 1963 that my advisor gave me. You can't read them, but majority of the materials that we use today, and I was talking to him about your tungsten carbide, it's in this book. It was practiced in 1960s. It was actually union carbide, the Praxair thing, right? So even though you make lots of improvement, it's very hard to insert a new idea into this thing. And of course, the implementation. And then second thing is knowledge and education barrier. This is what I've been focusing quite hard on, because thermal spray is called a special process. It's like plating and all of these processes. And what happens with special processes that you don't, it's not taught in colleges, right? So you have to kind of learn on the job. And if you can't learn on the job, then how do you practice these things? So then there's lots of attempts to try it in fuel cells and electronics and sensors and all that. Nothing worked because that knowledge just wasn't there. So this is when you start to think about why, and I'm giving you sort of a retrospective, and then thinking a little bit about the future, right? If this curve doesn't go this way, investors are not interested, because if you're doing it this way, it's called a commodity. And you don't need a PhD or a master's. You may not even need an engineer to do this, right? You have to keep pushing the envelope above in order for you to have your own survival, right? So I spent a lot of time trying to understand this agenda. So let me try to place it. So this is easy, right? Market need, I give you example, system driven, makes a product. You still have to do a lot of work to get there, right? Design, prototype, test, validate. That's like that landing gear idea, right? You have to do a lot of these things. Then you have to set up vendors. You have to write product specs and processes, and you make a product. That takes time too, but it's at least a sure thing, sort of. But we are here, right? You're at university, you do basic research, or you come up with a great idea, like a disruptive idea, like an iPhone or something like that. But then even here, you have to do applied research. And usually what happens is, by the time it gets adapted, remember this time, this is like a bridge that is never, you don't know how long the bridge has to be. That's why we call it the valley of death, right? So this is where most of us stumble in order to go forward, right? Lots of hurdles that you face, and I've faced this. So we go back and I'll show you how we are trying to tackle this problem. First is the science part. I'll get a little bit into that. So thermal spray is very complicated, not taught in colleges, because everything happens in non-equilibrium. So you got melting going from near ambient temperature to melting point, and maybe vaporization point, acceleration, and then quenching, immediately rapidly solidify. All both happen in the same place. There are very few processes that both happen at the same time, right? And then you got these very highly constrained structures. There were lots of stresses, and they are multi-scale, right? I remember one of Ashutosh will remember Vladimir. We gave him a coating, and he had a terabyte worth of images. I said, what are you going to do with all these images? It's like taking phone pictures on your phone, you never look at it, right? That's one of those things. Unless maybe AI will take care of that problem for us. And you can see this is really amazing. This 1 million frames per second was taken in Japan by my former postdoc, but you can see this is zirconia particles impacting a surface and splashing and things of that kind. So you won't see any of this standing outside the spray cell. So we call it spray and pray, or pray and spray. If you're religious, you can pray first and then spray. So the structures this is a kind of a gross example, but there's also some beauty in these structures, and how do you take advantage of them, right? So first we said we're going to look at the process completely differently, and I won't get into the details, but non-equilibrium, multi-scale, I already covered it. So we went to so we said we need a new science. So we went to National Science Foundation and said, we want to study materials formed from extreme conditions. First we said we wanted to study thermal spray. They rejected us. And 2 years later we went back and said, we want to study materials from extreme conditions. What does that mean? Well, we wrote a nice proposal, and we convinced them to fund us what's called the MERSEC, which is a kind of a prestigious award, and said we'll bring in new science into this whole idea. And that was a big thing. We got the first attempt and the second attempt, first round and second round. So the whole was about 12 years of funding, a lot of money, about $1 million a year. And then along the way, we developed some other cool technologies. And so what it did was it allowed us to bring fluid mechanics, solid mechanics, geosciences, chemistry, physics, heat transfer, solidification, everybody together. We had a whole big team of faculty from the various places, not just at Stony Brook. And they brought lots of fresh ideas, and also allowed students to be taught these new perspectives. And so that was a really an amazing thing, right? And so we tackled each block sort of individually. There was these different groups. We call them interdisciplinary research groups. And we introduced, the time that I was directing it, I was very painful to some of my mechanical engineering friends because they would come and throw me all these models. I said, well, is it real? Did you include this? Did you include that? But nevertheless, it still added a lot of value, right? New ways to characterize, new ways to measure, and that's something that we're doing now. We built a nice facility with it, and we trained lots of people with it. And they still remain friends. That's one of our nice things, because the former students also helped me take care of the facility. So we needed to come up with a way, so what's the purpose of all this science? So we presented all of this once to our industrial group. And they said, this all sounds great, but how does it affect us? And so I went back and I couldn't sleep that night and said, okay, how does it impact somebody? And so we had to come up with a new way. So I coined this term. I called it Partnership for Accelerated Insertion of New Technology, and my colleague Chris says, that's paint, and we're a bunch of spray painters, so it kind of made sense from that. So the idea was to bridge fundamental research with engineering practice. We wanted to be true to our mission that we're doing fundamental research. There's a lot of words here, I'll skip it, but basically both industry and the university have to think different, right, in this to do this. So I go back to the word value. You have to show value for what you do. You have to convince that the science is robust, and you have to convince the industry that they should use the science. And then you have to change the way the workforce thinks about the future. Have we been successful? Partially. I would say when people change jobs, it dies with them. And so the idea is we call this a three-plane chart. So we work here, we work together with industry here, and that's what the industrial needs are. This is a pretty common chart that National Science Foundation uses. So linking research to practice. But since we are a platform technology, we couldn't just do work for one company because they would never give us the money. So we made it pre-competitive. That means you work at that block below. We worked on industrially relevant materials, but our focus was our products were scientific, right? Whether it's the process structure property relationships or these methodologies. And so you can do what you want in the scientific framework, but what you want to do is translate that to value. So what does the industry care about? They want efficient, reliable, controllable process, like that cylinder bore example I gave you. Or if you're going to introduce, you want to come up with better ways for the industry to use the materials knowledge with better confidence. So if you can do these two things, then you increase applications. They're happy, they give you money. It's as simple as that. If you don't give you value continuously, then you won't get that. And we know we're doing something right because it's 22 years. Right now I'm bored, but they're very, very happy, and they want me to keep having these meetings. So, but it was not easy. How do you take all this and make it easy for them to understand? So this is busy, but let me get into the model. The first thing happened was we would do all of these nice experiments and present. They would come every 6 months to meet with us. And they said, this is too hard for us. Then I made a challenge to them. I said, give me 3 days of spray cell time. We call them booths. And I will show you how you can use the science. And I won't get into the details of it. We were using these beam curvature theories. And I sent my students to the company. And the idea was they would do their production applications, but we'll do the measurements. And in 1 week or 10 days it was, they went to 3 sites and did 80 experiments on site. And the idea was that they'll come back and they'll present it to the rest of the members. At that time, we didn't have that many members. It was such a success. And basically what happened was we took, these are all details and this is too much for this audience, but we took some very interesting fundamental science observations. We went to the factories and demonstrated, we showed how we can make processes both efficient and reliable. The 2 magic words for industry, right? We presented this at the next meeting, then my phone started to ring. We want a field trip, we want a field trip, we want a field trip. We started doing a lot of these, and then I said, it's enough, I can't do your work for you. And so, but then the methodology caught on. So that's the whole point I'm trying to make. So the point I'm trying to make is, if you want somebody to understand value, you got to go do it with them to get that to work, right? So here's some examples. I want to give a shout out to Jaya here. So the industry just measures things in very low, what we call CPK values. You want to measure if the coating is stuck, you put a glue and you pull it apart, right? It works, it's very easy to do, but there's not much science here. The science is very complicated. And so when I came here on my sabbatical, Jaya and we worked on, can I come up with a technique that is scientifically rigorous, but high throughput for industry to use? The stuff is still going on, but one of our members is funding IT. I call it ITM by mistake. That's one example. I'll go into the second example on these thermal barrier coatings. And I want you to understand, this is all details, but you see how many things, starting from phase analysis, to scattering techniques, to sintering studies and nonlinear properties, to thermal effects, and to environmental effects. It's 5 decades worth of work. So if you're a young engineer and you join a turbine company now, how do you know all of these things, right? So I'll give another simple example. So the industry, they find ways to solve problems. They're always very, very good at that, right? So they use 2 types of these coatings. One is a classic porous and one with deliberate cracks. Most people think of cracks being bad. It turns out in this example, the cracks are actually very good. And this is very popular. It's widely used. But people really didn't understand how these cracks form. So I had a PhD student, Shalaka, who, I won't go into the details here, but figured out what's the theory behind how these cracks form and how we can control it. And these are all published. So now, all of a sudden, we know how to understand and control these agendas. So how can I use it? So I'm kind of going a little bit backwards here. But I told you these engines, they are not just, we call them vacuum cleaners. They pull dust, especially in India and thing. Very dusty environment. So imagine all of these are coming into the engine. And they cause these coatings to be removed. Some compositions work, others don't. But there are lots of mechanical, thermomechanical, thermochemical. That's why I said, you should have a undergraduate program on gas turbines or just TVCs. It'll be enough to teach everything as part of it. So the current approach, if you come up with a new material, it'll take you 3 decades to get there. It's too long because you have to design the system, find the material, the right bond coach for the material. Then you got to process it. What's the correct architecture? How do I test it? Then after I prove all of that, then maybe somebody will put it into an engine test. And until it's done in engine test, it's not going anywhere. So it's enormous amount of it. So what you want to do is you want to think concurrently and introduce science where you can. So this is our top is where we are working. Let's say there is some work that Ashutosh worked on in UCSB, and now we worked on the processing side using some nice instruments. Somebody studied the failure mechanism. Then in the industry side, they worked on new materials, process, testing. And so you really want to bridge these two things together, and then that'll help you facilitate. And again, Ashutosh is doing some work with Pratt & Whitney on this idea. And one of the interesting things that came out of our scientific thinking is using all of these models and mechanisms is we actually designed a multi-layer coating. And the details of that is, I can send it to anybody that is interested, but the idea is that you can compute what is the optimum structure. And remember I talked about the cracked coatings? And we built this. This concept was demonstrated about 10 years ago as a viable scheme, maybe in 2015, 2016. Then I went shopping. I said, who is willing to test this? We think it's going to work really well because we had all the theory and the thing. So the first company said, oh, first we got to test it. So we gave them samples. We made the sample. GE did the test. Siemens did the test. Praxair did the test. And we showed them that how our material actually, in their benchmark testing, works really well. So then we went to one of the spray shops, said, okay, this is an interesting idea. They went and benchmarked, and in fact, they didn't do our multi-layers correctly, so two of them were stacked improperly, so they failed very quickly. But then the one that never failed, you see that arrow is still going up. They got encouraged, they actually made the part, and now it's running in an engine for the last 3 years. It's actually running in a power plant. So we know it's working well because they do what's called boroscope inspection. But again, it's about 10 years from concept to idea. The last example, and I'll finish in a couple of minutes, is you can also do these for lots of functional applications, fuel cells, lots of atoms, phosphors, one of them we were successful, dielectrics in the semiconductor, sensors, thermoelectrics, and so on and so forth. We had a big program to take a paintbrush, which is what thermal spray is, and make a thermal spray pen. We got a lot of money to do, it's called a disruptive technology. Remember I talked about basic research? So DARPA gave me money, says, can you make me a plasma spray pen? And I said, it's impossible. And they said, we'll give you some money to try. I said, then it's possible. And then after we finished, of course it was going to work, right? But it took a lot of effort. I don't know whether this video will play. I don't think it does, but I guess it's not. But basically, it's called direct writing. So you can go from a CAD to a part without a mask. You can write a thick film circuit. And because we can do that, now we can print on complicated shapes. So this is what they call a smart turbine component. So the idea is to put a thermocouple inside the thermal barrier coating and record what the real temperature is. Great idea, a lot of work, still not been implemented. But other things have implemented, like this is, for example, is a metallic conductor that's been deposited on polymeric film, which is very hard to do from thick film technology, and ours works very resilient structure. So this is now being used in industry. And there are other things that we are trying. Again, this is basically 3D printing circa 2000. So it's about 20 years ago. And the problem with all additive manufacturing techniques, they're fantastic to do research, but difficult to scale. So that's something to keep in mind, because if you want to make lots of machines, you have to keep investing. And the second thing is the machine shop people are not sitting idle. So any clever idea you got, you inspire them to compete with you. And that's sort of what happened. People started to use masks and compete with us. So finish off. First, it's an industrial technology, and academics followed later. Usually in those circumstances, it's easier to do things. Easy to do, but hard to perfect, right? Coatings are not always designed because they don't know how to incorporate properties. How do you design? And then the education, nowadays all these companies, they ask me to teach thermospace courses to their employees because nobody's even learned that stuff in their things. So, what do I mean by science-driven technology? It's like a tree, right? The more you learn, the higher the tree grows, right? And so what we are trying to do with our partnership with industry is to do methods, measurements, models, and mechanisms. So we're not competing with anybody. And so the idea is that hopefully will open up new opportunities. More important than anything else, it gives enhanced confidence and extended capabilities. And so that's the bridging. It's not just science and technology. The most important, in my view, is education and human resources. I won't get into the details, but that's with that, let me stop and thank you for your attention.